Okay, good morning, and today we are going to discuss about enhanced readout scheme for bitline driven 1T 1C DRAM. So let me go into the introduction. So next 50 minutes we are going to discuss about this enhanced readout scheme for 1T 1C DRAM and why we change from traditional DRAM to the enhanced DRAM. So coming to this traditional DRAM, the primary principle relies on charge sharing between the bit line and the cell capacitance, followed by sensing with a differential sense amplifier which is already with some reference voltage. So if the bit line capacitance voltage is greater than the reference voltage, then the output node is pulled to the VDD. Uh, if the bit line voltage is less than the reference voltage, then output is pulled to the ground. And next come to the primary principle relies on this proposed scheme is that the charging of both bit line and the cell capacitance to specific voltage and comparing this charging current to a reference current of this current comparator. So if this current of this bias voltage is less, so basically, if this charging current is less than this reference current, then it will sense as logic 0. If the charging current is greater than the reference current, then it will sense as logic 1. And next coming to this conventional readout scheme. So it basically consisting of 1T 1C configuration. So and also connected to the bitline capacitance and followed by sense amplifier to amplify small voltage differential on this bitline capacitance node. So it basically followed with the pre-charging and equalizing bitline voltages. So the sense amplifier detects these tiny voltages created by charge sharing from this storage net capacitance. So let us take an example to understand this. If we have any voltages on this storage node capacitance, let us say VDD. So after asserting the word line, this axis transistor is turned on and the charges from storage node uh, uh, start uh, start flowing from flowing via the axis transistor to the bitline capacitance, as results of which the reference voltage will be slightly increased to some delta V sense margin. So this voltage is fed to the sense amplifier and which will be compared with the uh, 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 bitline reference voltage. If this is greater, then it will be pulled to VDD. If it is less, then it will be pulled to the ground. So now in the case of storage of logic 1, it is slightly greater than VDD by 2 plus delta V. So it is greater than reference bitline voltage such that it will be pulled to VDD, and this voltage is again fed back to this bitline capacitance and still this axis transistor is turned on. So now again the capacitor will restore its value back. So that's why we call it as this DRAM as the dynamic random access memory. So there is dynamic refreshment is required in this particular uh, uh, um, particular memory. So it basically have different phases. So first it will be having the pre-charge phase, and next it is having the word line activation and sensing and restoration. I mean restoring the storage node capacitance value. So this is basically typically this is the schematic of this conventional sense amplifier with 1T 1C. So let us understand this operation of this complete overall circuit. So let me start. Let us assume that this CBL storage node capacitance is storing the value of VDD. That means which is basically known to be a logic level 1. So before, whenever we want to read the value from the storage node capacitance, we will pre-charge the bitline capacitance to reference voltage, that is VDD by 2. So after pre-charging this bitline capacitance, we will assert this word line such that the voltage across this storage node capacitance uh, start discharging via this NMOS such that the voltage across this CBL start increasing. The If it is storing VDD, this reference voltage will be slightly greater than VDD by 2 and it is fed to this sense amplifier. Sense amplifier is here nothing but a cross coupled inverters. So after development of VDD by 2 plus delta V, which is sensing sense margin voltage, it will be fed to this bitline voltage. It is fed to this bitline uh, bitline node. So this bitline node is potentially connected to this PMOS and this NMOS. So this is VDD by 2 plus delta V. So definitely this NMOS is going to be turned on. I mean the overdrive of this NMOS is greater than the overdrive of this NMOS because this is at VDD by 2 and this is VDD by 2 plus delta V. So essentially the overdrive of this NMOS is greater than this NMOS. So this node voltage is directly connected to this ground such that the discharging of this node voltage is faster than the discharging of this bitline node voltage. As results of which, as this is discharging to the ground, there is a chances of turning on this PMOS. So at some point of time potentially this PMOS is going to be turned on and this VDD is appeared across this bitline voltage. Again this bitline voltage is uh, uh, so this bitline voltage is pulled up to the VDD and this bitline ref is pulled to the ground and which is essentially again given back to the CBL and still this void line is turned on such that this VDD voltage again right back to the CS storage node capacitance and it restores its value. That's why we call it as this DRAM cell is DRAM cell is dynamically random access memory, as continuous refreshment need to be happen in order to retrieve our data. Without it we lose our data. Next, coming on the other hand, enhanced readout scheme. So this enhanced readout scheme, what basically employs is that if the bitline as well as cell storage capacitance is charged to certain level, then the charging current in case of one storage will be smaller than that in case of zero storage. This is simply due to the initial precharge of CS in case of one storage compared to initial discharge of CS in case of zero storage. We will explain this how this is happening in the next slide, which we are having the schematic, and potentially we will dive into these simulations in TSMC 65 nanometers CMOS technology node. So next let us go to the circuit schematic of this enhanced readout scheme, which is modified form of that conventional DRAM cell. So potentially let us understand what a difference does this circuit created with respect to the previous circuit. So in the previous circuit, we are having this 1T1C as usual, and the sensing circuit is changed to the current comparator rather than voltage comparison, and another circuitry is coming with respect to if you compare it with the 1T1C conventional DRAM cell. So this external additional circuitry is mostly having one transistor in series with diode connected transistor. So let us understand what actually happening in this overall circuit by taking one example. So let us understand if we are storing some logic 1 at the CS node capacitance. Okay, if the initial voltage of the storage node capacitance is VDD. So now we turning on this control signal to some value such that this V precharge is potentially 1.2 voltage and this MOSFET is going to be turned on. And after that we are asserting this word line such that there is a path between CBL and CS node capacitances. If you turn on this, the current start flowing from V precharge, and at the same time the current also start flowing from the storage node capacitance. As a result of which the current from the CS node capacitance increases the CBL voltage, CBL voltages. And this CBL node voltages is connected to M5 transistor source node. As the current which is pumping from this V precharge flowing through this M5 transistor is basically determined by the uh, square uh, square law. So current square law. So that quadratic law. So now the current which is flowing through this M5 is basically determined by this M6 transistor. Now, as a result of current flowing from this storage node capacitance, there is some voltage development at this VBL node node voltage. So, as results of which, if this if the source node voltage is increasing, the VGS of this M5 transistor is decreasing. As a result of which, the current flowing through this transistor is decreasing, but the current coming from this transistor is increases. If this is more than this, then definitely this voltage is going to be increases. This V gate of this transistor is going to be increases in order to compensate this source node voltage to maintain proper equal currents from M6 and M5 M6 transistor. So as we are storing VDD across the storage node capacitance, so definitely the whatever voltage developing over here, it will decreases the VGS, as a result of which the current through this M5 decreases. In order to accommodate same current, this VG has to increase to balance out the both currents. So in case of storing one, the current which is pumping from this M6 is greater than which is flowing through this M5. As a result of which this node voltage will start increasing, and this node voltage is potentially connected to this current comparator to the M1 of the M1 transistor. So now the voltage is coming over here. So let us assume, let us have a feel for this, and assuming some values. If it is having some 650 millivolt and the voltage developed over here is some 670 millivolt. As a result of which this overdrive voltage is greater than this overdrive voltage. As this is biased previously, the current through this transistor is already defined. That is which we call it as reference current. And this now the voltage coming from this uh, drain of this M5 transistor to this M1 transistor will turn on this M1 and some current flows through it, and this overdrive voltage is basically greater than M2 transistor, as it is only 650 millivolts and this is 670 millivolt. Now after turning on this output bar is tried to discharges to the output bar node voltage is discharges through the ground. As this is turning on, the current also more to this M1 transistor than M2 transistor I reference, as results of which this output. So this overall current comparator is mainly handled by this CCA control signal. So if you assert this CCS control signal, this will turn on this upper PMOS transistor and the lower NMOS transistor respectively. And if output bar is trying to discharge through the ground, this output bar is decreasing, as a result of which this M4 transistor tries to turn on. At some point of time, this M4 transistor turns on and this VDD pull down to this output node, and that's how we sense the voltage stored across this capacitance is logic 1. As we know that as this voltage is pulled down to the VDD, then this transistor turns off respectively. So now compared with that conventional DRAM cell, there is a difference in this readout scheme. As we know that we have seen that in conventional DRAM cell, the storage node capacitance, for example, having some logic 1, it requires some time. I mean, some sensing voltage delta V has to be developed across this CBL. V plus delta V. So in order to create some delta V, there is some time required in the case of conventional DRAM cell. But in this case of this enhanced readout scheme, what basically is happening is we are not relying on this 1T 1C DRAM cell. Instead of, we are completely relying on this node voltage. So this node voltage is what actually determines the complete sensing of this 1T 1C DRAM cell. So this node voltage has to be preserved with respect to VTH and V precharge voltage as well. So this signal is basically here will do the job of that. Like if any voltage is present initial starting of this overall operation, this signal we will provide some this signal to this transistor. This is like a so this will act like a switch, and which we will potentially give very high W by L to discharge this node fastly. So when we assert this signal, the node voltage, whatever it is there initially before starting of the operation, will discharge to the ground. So now coming to this, in the case of storing the zero, the similar operation will happen. But the thing is, this node voltage will not increase as the charging current will pump more over here rather than pumping from this M6 transistor. As this Vs is less and the Vg is more, so the Vgs of this transistor is more, so the overdrive of this M5 is more, and potentially the current flowing through this M5 is more. So the current coming from this M6 and the current flowing through this M6 is more, there is a difference. So in order to accommodate a balanced current, this Vg has to decrease in order to maintain same current which is flowing through this M6. And again this is fed to this current comparator, and there is a reference current already flowing through this. If the voltage is less than, let us, I said already 650 millivolts, and this will be potentially 630 millivolts, and then the this transistor overdrive is less than this, and this output node voltage will discharge to the ground faster than this output bar. As a result of which this PMOS will turn on and the VDD will be appeared over here, and this output is pulled to the ground such that we will sense it is storing the logic 0. So next, coming to this methodologies which we will discuss to compare both enhanced and this conventional DRAM cells. So first, coming to this conventional and enhanced readout scheme, the primary focuses we are putting mainly on this performance, area and the power consumption. So all above aspect will be verified with the simulation CMOS 65 nanometer technology node. So coming to this performance comparison will be discussed by my friend Vikas.
So yeah, here we will discuss the performance comparison. Here we will see the some simulation results of the conventional scheme and our proposed scheme. So yeah, first we will see the conventional scheme read speed. So here we are reading 0 at 24 nanosecond. First what happened? First pre-charge phase will come. After resetting word line, small bump will come, and after small bump will come, we reset our sense amplifier, and after our that bit line voltage go to 0. Similarly, in case of reading 1, similar operation will happen. Pre-charge phase first will come. After it, asserting word line, small bump above bit line come, and after it, sense amplifier activation, that bit line goes to reading 1 at 23.37 nanosecond. So yeah, here we will discuss our enhanced scheme read speed. So first we are seeing here our control signal and activation of word line are activated simultaneously, and after getting enough voltage at the our diode connected voltage which is fed to the our current comparator, we are turning on our current comparators, and so that it will compare the current with our reference current, and after it will go to your it will read 0 at the output. Similarly, like for reading 1, same control and word line we are setting simultaneously. and after getting enough voltage at the diode connected drain voltage, which is fed to the current comparator, which is more than your reference current, and that's why our current comparator give rise to reading 1 at 4.75 nanosecond. So here we will see the area comparison. We will compare our area by analyzing the layout. So here first we will see the layout of our conventional scheme. This is the layout of conventional sense amplifier. Here we can see the marking of our scale, which is showing our width 5.2 micrometer and length of 5.3 micrometer. So overall area, if you multiply, then it will come to some close to 27 micrometer square for our conventional scheme. And we tested our DRC check also, and we cleared our all metal to metal spacing error, and most of the error we cleared. And after that we come to LVS check. LVS check, here one error is coming here, which is fault of our like missing instance. There's some incorrect file in our cadence 61 nanometer. So that's why one error is coming, but all the connections are correct. So yeah, here we will see we are seeing our enhanced scheme layout. So here we are seeing our current sense amplifier and with that extra circuitry layout. So here we can see the scale marking of width of 5.1 micrometer and a length of 9.8 micrometer, which is very high as compared to our conventional scheme. And if we multiply our width and length, then we'll get our area of 47 micrometers square. Here also I checked LVS, but here all the LVS is coming correct because we used NCH and all LVS are coming correct. So yeah, power comparison. Here we will compare the power of our conventional scheme. We compared power of the both scheme by doing transient analysis, and we got conventional scheme power is 13.2 microwatt and enhanced scheme power is 60 microwatt, which is very high as compared to our conventional scheme. So here we will see the comparison table for conventional and enhanced scheme. For reading 1 and 0 for conventional, we are getting 24 nanosecond, and for enhanced 4.6 nanosecond, which is very small as compared to our conventional. Area is small in our conventional, that is 27.56 micrometer square and 50 micrometer square in enhanced scheme. But power delay product is less in our conventional scheme, that is 320 femtojoule, and enhanced scheme we have 276 femtojoule. So from here, my friend Raj will explain the array level testing for conventional scheme. Okay.
So here we will explain array level testing for conventional scheme. So here we have used 8 cross 8 array, DRAM array, and to decode that we have used a 3 cross 8 decoder, which will be used to select particular word line for the read or write operation. So this is the test bench that we have made. This is a 3 cross 8 decoder, which means there will be 3 input pin and 8 output pin, which will be decoding the word line which are needed to be accessed at that particular time. So yeah, this is the simulation result of the test bench decoder 3 cross 8. So as it is a 3 cross 8 decoder, so there will be 3 input. So we have considered M2 as so here we can see that if you take the combination of 0 0 0, then your D0 will be high, and if you take 0 0 1, then your D4 bit will be high, and similarly if you take 0 1 0, then D2 will be high. So this is the result of the test bench simulations of the decoder. Okay, so the D4 will be high when our input combination will be 0 0 1 and 0 0 1 0, then D2 will be high. And here we have taken A2 as MSB and A0 as LSB. So yeah, this is our 8 cross 8 DRAM array. We have made this 8 cross 8 DRAM array, which is so this 8 cross 8 array is for conventional sensing scheme, and here this is a 3 cross 8 decoder, And here, as you can see that these are the sense amplifier, which will be sensing the bitline voltage, change in the bitline voltage. And as we know that this decoder will select any one of the word line of these eight word line. So here we have taken an example how we are reading. So we have selected one word line, and then in that particular word line, this bit line 0 we are reading, bit line 2 and bit line 3. So bit line 1 is going to 0, and this bit line 2 and bit line 2 is going to VDD. So this is the another DRAM array, 8 cross 8 array. This is for the enhanced scheme that we have using. And see, these are the sense amplifiers, and this is the decoder, 3 cross 8 decoder, which will select any one of these word line, and then the sense amplifier will detect the change in voltage in bit line, and according to that it will give the output. So these are the simulations result. So this is again the simulation result of our enhanced scheme. So here we are asserting this control and this activation word line. So we can see that here we are trying to read row 5 column 1, row 5 column 3, and row 5 column 5. So we can see that this row 5 column 1 is going to high value, that is VDD, and this row 5 column 3 is going to 0, and this row 5 column 5 is going to again VDD. So conclusion. So in conclusion, we have successfully simulated and tested our conventional and enhanced readout scheme. So the result shows that the enhanced readout scheme reads logic 0 and 1 approximately 80% faster than the conventional scheme. And the power delay product is enhanced by 23% better than the conventional scheme. So these are the references that we have taken, and
Thank you all.
so this is all for this our project and PPT. Thank you all.